Last class we gave a sort of algebraic or matrix proof of the fact that only these symmetry axes can be part of a crystal. Only these 10 symmetry axes can be part of the crystal. So, these themselves are 10 point groups. These are 10 point groups, because as you have seen that when we say a fourfold axis, it is actually 4 different operations: an identity operation which is a 0 degree operation, then 90, 180 and 270. So, these 4 operations we have seen form a group. So, 4 means it can mean different things. 4 can mean a number 4, or 4 can mean a fourfold axis. So, that is the geometrical axis, or it can mean the point group operation 4, point group 4, which means the 4 symmetry operations or 4 rotations which are associated with this point group. So, these 10 symbols 1 to 6 and 1 bar to 6 bar represent 10 different point groups out of 32 3 dimensional point groups. So, you have already now met 10 point groups. As we proceed in the course, we will try to meet the other 22 point groups which are not in this list. So, that matrix or algebraic proof we gave, this class we will visit a geometric proof for that, the same thing, because algebraic proof we never drew any lattice or vector or anything. There was just a matrix, and we decided that the matrix is made up of integers, and we decided that, or not we decided, we proved that the trace of the matrix is 2 cos theta plus 1, and since 2 cos theta plus 1 became integer, you found that only these 5 symmetry rotations are possible, or 5 symmetry axes are possible: 1, 2, 3, 4 and 6. We did not prove 1 bar, 2 bar, 3 bar, but that is left as a simple exercise for you. The proof is simple, because all you have to do is to multiply that matrix with the matrix representing inversion, which is which will multiply all the diagonal terms by -1. So, you will again get the same result. Instead of saying 2 cos theta plus 1 is an integer, now you will say negative of 2 cos theta plus 1 is an integer, but finally you will get the same axes. But of course, there is one new thing which came in 1984. Crystallography is much older than that, more than 100 years old. So, this theorem and all are more than 100 years old, but in 1984 there was some sort of revolution or shaking of foundation of crystallography. That is what the kind of news which was coming. It was nothing like that, but it was a new discovery, and where they were finding that there are crystals with 5-fold symmetry. That was the original discovery. Later on, 10-fold symmetry, 7-fold symmetry, various kinds of symmetry groups started coming in. So, I put crystals under inverted comma because they are not really crystal, and that is why the adjective quasi was prefixed to crystals to distinguish them from true crystal, which we are discussing in this course. So, they are not true crystal, and if they are not true crystal, then they are not restricted by this crystallographic restriction theorem. So, that is why they can have so called non-crystallographic symmetry like 5-fold axis or 10-fold axis, 7-fold axis and all. We will also discuss the phrase group. Phrase group is the first group. Now, we will start where we will start thinking of combining translations with point symmetry, because after all periodicity or translational symmetry is the essential symmetry for crystals. So, unless and until you have the translational symmetry, you do not make a crystal. So, point groups only give you symmetry of finite objects. So, a square, for example, a square is not a square crystal, but a square has a 4-fold symmetry. So, it has a point group 4. So, the symmetry of a square is more than 4, we will see, because it has mirrors also, but not thinking of mirror. If you are only thinking of rotation, so it is not right to say that the symmetry of the point group symmetry of a square is 4, but the rotational point group symmetry, that is ignoring mirror reflections and so on, is 4, but it is a finite object, it is not a crystal. Crystal can also have 4-fold symmetry, as we are seeing, because this was obtained by combining them with translation. This restriction came because only these symmetry operations are consistent with translation. Otherwise, this restriction is not there. A finite object pentagon is there, you know that. You can draw a regular pentagon, it will have a 5-fold symmetry. So, it is that nothing can have 5-fold symmetry is not what we are proving. Nothing which has translational symmetry can have 5-fold symmetry. So, it is the translational symmetry which is putting this restriction. So, the phrase group is objects which have one dimensional translational symmetry. So, we will see that crystals have 3-dimensional translational symmetry. We are looking at tilings, 2-dimensional tilings also, which have 2-dimensional translational symmetry, and we can limit to 1 dimensions, then you get a phrase group. So, phrase group, if you define, these are 2-dimensional patterns. So, pattern is 2-dimensional, you are drawing in 2D, but the translational symmetry is 1-dimensional. 2D patterns with 1D translational symmetry. So, let us look at first the geometric proof of our crystallographic restriction theorem. We will first prove that perpendicular to any rotation axis, that is, in a crystal, if you have a rotational symmetry axis. Now, you have already seen that, no, you have not seen, you do not know, because we will not use the matrix proof now, we do not know the proof. So, we do not know that 5-fold does not exist, we want to come to it another way. So, we know that some symmetry axes can be there in a crystal. So, let us say that this is some rotation axis, and if it is a crystal, it will have some lattice translation. So, let us draw that lattice translation. So, I am trying to be general. The lattice translation could be parallel to the axis or perpendicular to the axis or at an angle. If it is perpendicular to the axis, then there is nothing to prove, if you assume that there is a translation perpendicular to the axis. So, that is why I am making an inclined translation, not assuming that this is perpendicular, but later on we will say that it will generate or show that it will generate a translation which is perpendicular also. So, OA is a translation, OR is the rotation axis, and since it is a rotational symmetry axis, it will rotate things around it. So, if OA is one lattice translation, to maintain the symmetry, there should be another. If I rotate this by whatever n fold it is, I should get, after one operation, I should get another lattice translation OB. So, A to B you are going by the rotation of 2 pi by n, because that is what is meant by the n fold axis. So, if OA is a lattice translation, OB is also a lattice translation. But then if you have two lattice translations, then if I join the vector A to B, what is A to B? That also has to be, if two endpoints of two lattice translations are joined, that is also sum or differences of all lattice translations will be lattice translations. So, OA is a lattice translation, OB rotated lattice translation, AB is OB minus OA, which is a difference. So, that is also a lattice translation. Means they will always take you from a lattice point to another lattice point. All vectors do not have this property. So, we are talking of very special vectors, which if I put the tail of any of these vector at a lattice point, the head will also be at a lattice point. Now, what can you say about relation of AB to OR? Is AB, orientation of AB related to OR? It has to be perpendicular in any rotation, because it will form a surface of a right circular cone of half angle theta. Okay. So, the circle which I have drawn, the rotated vectors have to be on that circle. So, that is on the base of this cone, and OR is the axis of the cone. In many ways, means I am just giving you a hint, many ways you can show that AB will be perpendicular to OR. In 2D pattern, this was trivial because your rotation axes were always perpendicular to the plane of your drawing, but in 3D this was not obvious. But in 3D also now you know that whatever orientation your rotation axis is, if it is a symmetry rotation axis, there has to be some translation vector which is perpendicular to that axis. This part is usually missed in books, so that is why I gave you. You will use, because most books will start with this part B, but this part A is required because they assume. So, they will say that okay, now assume that O is my n-fold axis and let OA. So, now O is an n-fold axis perpendicular to the plane of the drawing. So, I am not drawing the whole axis, I am only drawing the intersection of the axis with the plane of my drawing. So, the axis is going through O and is perpendicular to the plane of drawing. And since it is a lattice, from our earlier proof from part A, we know that there will be a lattice translation in the plane of the drawing. So, that lattice translation we are calling OA, because the plane of the drawing is perpendicular to the axis, and we have just seen that perpendicular to the axis you are assured to find a lattice translation. Now, if it is an n-fold axis, then you know that theta min is 2 pi by n. So, n-fold axis will rotate this lattice translation by this theta min. To give you vector OB. It can rotate both clock. When there is a n-fold rotation, you can rotate plus 2 pi by n or minus 2 pi by n, because anyway there is a symmetry group and rotation can act both ways. So, you can go the other way around also. Now, you can add these two vectors. Counterclockwise. Clockwise, and then we are having OP, which is sum of OB and OC. And again by the same understanding, since OA was a lattice translation, OB is obtained by a symmetry rotation. So, symmetry rotation should take a lattice translation to another lattice translation. So, OB is a lattice translation, OC is a lattice translation, and OP, which is sum of two lattice translations, is also a lattice translation. And again I leave some geometrical steps for you. It is easy to show that OP is, what is the relation of OP to OA? They have to be parallel. Prove that geometrically. Now, we had not made one assumption, let us make one extra assumption that OA is shortest lattice translation. If you have a lattice translation perpendicular to any given axis, some of those lattice translations will also be lattice translations. So, actually there will be infinitely many lattice translations along that. But since it is a lattice translation, there will be a minimum lattice translation in any given direction, because you can't have a smaller and a smaller and a smaller going to 0. So, there will always be a shortest lattice translation. So, we should pick that particular lattice translation. We are assured here that there are lattice translation perpendicular to the axis. Among those lattice translation, I choose the shortest one. So, OA is my shortest lattice translation. Now, can you find OP? So, let us say the length of OA was A. So, OB will also be A, OC will also be A, and how can I write OP in terms of A and theta min? 2A cos theta min. But if A was a shortest lattice translation, what should OP be? N times the shortest, because you can only add the lattice translation. So, if you have the shortest lattice translation A, the next larger lattice translation will be 2A. You can't have 1.5A. So, 1A, 2A, 3A, that's how you will go. So, OP also has to be equal to n times A, where n is an integer. So, again you can see now you have a restriction on cos theta coming from a different way of analyzing. So, you have 2 cos theta min, 2 cos theta min is equal to n. Slightly different formulation you see. There we got 2 cos theta plus 1 is equal to n. But if 2 cos theta plus 1 is equal to n, won't 2 cos theta will also be another integer? Only you have to subtract 1. So, this will also give you exactly the same 5 axes as the previous one gave. So, again theta min will be either 0 degree or 180 degree, so 120 degree, 90 degree, 60 degree, that is all. No other values of theta will satisfy this equation, they will not give you an integer value. So, that is in terms of the fold of the axis 1, 2, 3, 4 and 6. So, that is whatever proof satisfies you more, you can look at it, but it is nice to look at it in more than one way, the same result.